So we're going to continue studying about radicals, and we're going to learn specifically today how to simplify radicals using a set of rules. Now let's first review properties of radicals that we learned early in the year, but we learned them just with square roots. So you remember that when we had the square root of 2 times the square root of 8, we were allowed to make that the square root of 16 so that we can simplify to that to be 4. Now we're also going to apply that to cube roots. So cube roots can be simplified the same way. Now notice that these indexes have to be the same number. That's what these rules over here tell us, that the nth root of AB has to be the same if I can split them apart or take them from a split product into one radical. So you could see here I have the cube root of 3 times the cube root of 9, neither of which can be simplified first, but if I multiply them under the same radical, then I can cube root those, the 27, to get 3. Now that rule also applies with the quotient. Quotients can be split apart as long as the index are the same. Now again, I want to reiterate, we cannot add or subtract under roots. So if I have the cube root of 2 plus the cube root of 3, I have to leave it separately. I cannot make this the cube root of 2 plus 3. It will not work. So make sure you remember that this is only for products and quotients. Now, I'm going to talk specifically as we get through some examples of the difference between if our index is positive, or I'm sorry, if it's an even value or if it's an odd. With odd values, there's no restrictions. We know like the cube root has all real numbers in its domain, but an even root function cannot have negative values under there. So I'm going to show you how to handle that in our second set of examples today. So let's look at the rules that we're going to have to look at. So of course this diagram is just explaining all the parts to a radical. So we have the radical sign, we have the piece underneath that we know is called radicand, and now we have this number here that's called the index. Now this first rule, I put a little check by. We're not going to actually need that for a few lessons. When we get into rational exponents, we are going to simplify that, but for the next few lessons, we're going to be stuck on this second, third, and fourth rule. The second rule says that the radicand contains no factors that are nth powers of an integer or polynomial. What that means is if this index is a square root, then I can't have any perfect squares left behind. We have to simplify them out and pull them out. The third rule is that the radicand contains no fractions. So if it has a fraction under there, we'll have to split it apart and separate it and simplify from there. And then our last rule is that no radicals appear in the denominator. So if radicals appear in the denominator, then we're going to have to do a process called rationalization. So when we rationalize, that's going to get the radicals out. So let's look at our first example. So it says simplify the square root of 25, a to the 4th, b to the 9th. Now let's remember that if there is no index, we can assume that the index is 2. So now I'm going to split apart the pieces. The square root of 25, the square root of a to the 4th, and the square root of b to the 9th. Now I can simply do the square root of 25 very easily. The square root of a to the 4th we might need to think about. Since it is the square root, what I need to have for it to come out is they have to be perfect squares. Well, if I break a to the 4th apart, I actually can break it up into 2 perfect squares. And I can do the same thing with the square root of b to the 9th, except b to the 9th is going to have quite a few more. So I break it down until I have 9 b's in total. So right now I have 2, 4, I have 6, I have 8, and I have 1 b left over to make me 9. 2, 4, 6, 8, 9 b's when I break them into perfect squares. Now I'm going to go ahead and pull out what I can. So the square root of a squareds are going to give me 2a's coming out. If I come over here, I have 1, 2, 3, 4 b's that can come out, and then I have 1b left behind. So let's recap what I have all together that came out. I have 1, 5, I have 2 a's, I have 4 b's, and I have the square root of b that could not come out. Now what I want to do is I want to check a couple things. Since my index is a 2, I want to make sure everything that came out was positive. So 5 is definitely positive. If I square whatever a is, that's going to be positive. If I take b to the 4th power, that's positive. So we're okay with our signs. Now, what we did was we pulled all the perfect squares out of our radical. Our radical doesn't have any fractions, so we met that rule. And no radicals appear in our denominator. So we are simplified. Now let's look at our second example. So I have a quotient, and if I look inside, there's nothing that I can do to simplify y to the 8th divided by x to the 7th. So I'm going to go ahead and simplify. Again, the index here is going to be 2. So I'm going to have the square root of y to the 8th and the square root of x to the 7th. Now, if I look at my index and my power, I hopefully am starting to see that I would have 4 y squareds in there. If I break this down, I have y squared, that's 2, that's 4, that's 6, and that's 8. Maybe you're seeing a relationship of division there. That means I'm going to have y to the 4th on top when I simplify and cancel out. On the bottom, I need to pair my perfect squares, x to the 2nd, that gives me 2, 4, 6, and I'm going to have 1 left over to make me 7. So I can pull 3 out, so that's going to give me an x to the 3rd, but I have 1 square root of x left. So let's start over here. I have y to the 4th divided by x cubed divided by x. Now if I go through my checklist, my index is a 2. I can't get it any smaller. I pulled out my perfect squares. My radicand inside has no fractions, except that I do have radicals in the denominator. So this is when I do a process called rationalization. I'm going to rationalize this. To rationalize, I'm going to multiply by 1. Well, when I multiply by 1, I get what I started with, except I'm going to multiply it by a fractional version of 1 so that I can get this square root out of the denominator. Now we see up here that it takes a perfect square to bring it out. So I'm going to multiply the top and the bottom by the same number. So it's just 1. But I'm going to multiply by the square root of x because that is going to pair with this square root of x in order to get rid of my radical in my denominator. Does it move to the top? Yes, but it is out of the denominator. So I have y to the 4th times the square root of x on top over this square root of x times the square root of x gives me 1 more x on the bottom. So now I have y to the 4th times the square root of x over x to the 4th. Now I check. My index is 2, and those are both even numbers. So I am finished. And now I've met the last requirement that no radicals appear in the denominator. So let's look at our third example. So this one is a cube root with a fraction inside. So I look inside to see if I can simplify. When I can't, I go ahead and separate the top from the bottom. Now I'm looking for perfect cubes to pull out so that I meet this second rule. No perfect cubes in 2, 9, or x. So I have met that rule. No perfect cubes in there. Now the radicand contains no fractions. I've met that rule. My third rule is that no radicals appear in the denominator. So we're going to have to rationalize this. In order to rationalize this, I need this time perfect cubes. So I need 3 of things. Now, if I break 9 down, I know that 9 will break down into 2 3s, and I have 1x. So that means to rationalize this, I'm going to need an extra 3 so that I have 3 3s, and I'm going to need 2 more x's so that I have x cubed. So this becomes what I rationalize. I'm going to multiply the top and the bottom by 1, but it's going to be the cube root of 3x squared on top and the cube root of 3x squared on the bottom. So that will give me on top the cube root of 6x squared, none of which are perfect squares, but on the bottom I'll have the cube root of 27x cubed. Now I know that both of those are perfect cubes. I'm going to come down here. That's going to leave me with the cube root of 6x squared divided by 3x, because the cube root of 27 is 3 and the cube root of x cubed is x. Now, since this is a cube root, I don't have to worry about any numbers being positive or negatives because they're all allowed in the domain. All right, now what I want you to do right now is I want you to pause this video and I want you to try these 3 problems. And when you're done, go ahead and start the video and check your progress. All right, so for the first example, I have the index of 2. So I'm going to split apart and make this the square root of 16 times the square root of, I'm going to go ahead and break those down into perfect squares as I go. I should have 2, 4, 6, 8, 10, 11 y's. Now I'm going to pull out what I can. The square root of 16 is 4. This is going to give me x squared. 1, 2, 3, 4, 5 is y to the 5th times the square root of y. I don't want to forget about him. He gets left behind. So I pulled all the factors out of my radicand that I could. My radicand contains no fractions and no radicals appear in the denominator. So everything seems to be okay except for one final check. And because my index is a square, I need to check to make sure nothing will be able to be negative. So I look, 4 is positive, x squared is positive, but this y to the 5th, because this is an odd power, that means it has a chance to be positive or negative. And because it has a chance to be negative, I'm going to throw a set of absolute values around him to ensure that he's always going to stay positive. So this will be my final radical after I've done the simplifying process. All right, let's look at our second one. So I'm going to go ahead and split this radical apart. Now this is a square root, so I'm looking for perfect squares. So I'm going to write the top as x squared times x. I'll write the bottom. I need 7 of them. So I have 2, 4, 6, and 1 left over to get me 7. So now I pull my perfect squares out. That gives me x square roots of x. That gives me 1, 2, 3 y's and a square root of y. So I fulfilled the second rule and I pulled out all my perfect squares. I don't have any fractions in my radicand, but I do have one in my denominator. So I'm going to rationalize. Now with the square root, I only need one more of what I have inside of here. So I'm going to multiply the top and the bottom. Again, I'm just multiplying by 1 by y, the square root of y. That's going to give me x times the square root of xy over, I have y cubed. This is going to give me an extra y, so I will have y to the 4th in the denominator. So I've got all of my radicals out of my denominator, and now I'm going to go ahead and check, since this is an index of 2, this x is not allowed to ever be negative. I'm going to put a set of absolute values around him. That y to the 4th will stay positive. All right, my last example here, I'm going to go ahead and split. I have a cube root of 8. Well, I do know that that's a perfect cube. And the cube root of 3y squared. So I can go ahead and pull that out of there right now. And that still leaves me with the cube root of 3y squared that I'm going to have to rationalize. So to rationalize this, I need 3 of everything. So if I have a 3, I'm going to need 2 more. If I have y squared, I'm going to need 1 more to get me 3. So I'm going to multiply the top and the bottom by 3 squared times y. And that's the cube root, because I have to keep my index the same. So now I have on top 2 times the cube root of 9y divided by, I have the cube root of 3 cubed, and the cube root of y cubed will simply just be 3y. Now, because this is a cube root, everything is fair game to be positive or negative, but this is as simplified as I get. Okay, so after you completed these 3, try the practice problems I left for you on Google Classroom, and if you have any questions, please let me know. I hope you have a great day.